Okay, let's get started. Good morning. The class looks lean today too. Okay, so the next homework projects and the assignment and the handout should be over there. And I'll try to put the next homework assignment and project online right now. So if you wanted to get a head start and finish those, that'll be good too. Because I don't want to have projects till the last day of class. So if you wanted to manage your time, it should be fine. Because I think the last project you can actually start pretty much along with this module, right? In terms of the material covered and stuff like that, right? So this is where the grades stand. So we have up to 54 points out of 100 right now. And I still have one person from quiz 1 and one person from quiz 3. I don't know, they didn't leave a name. And since many people didn't take the quiz, I couldn't eliminate and figure out who those are. So, and the next homework project, the homework project 3 was also graded. I think the TA gave it to the office this morning. So if you go later this afternoon, you should be able to pick up all your stuff. Pick up all your material. If you have any questions with grades, talk to me soon. And if you did the quiz and didn't get a grade, talk to me because I have 2 quizzes which don't have a person to it, right? And obviously, we still have almost half the class to go. And I do this, replace one of your grade with a median if you kind of mess up and stuff. So those don't apply at this point. And I tried to give you grades based on at least 1 percentage point drop. And interestingly, that happened at 90 and 80, exactly the round numbers, right? So right now, if I were to give a grade, like somewhere people who are above 90 would be sort of A, and above 80 would be like a A minus kind of stuff. There are still people here, especially somebody who's at 55, and there's not a whole lot I can do if you're there. And I mean, it's not like you're, I don't remember who that is, but it's not like it's over because we still have almost half the grades to go. So if you want to work something out, talk to me. One of the nice things about this class is there are so many data points, right? So you can't really argue that something happened, you had a bad day kind of stuff. I mean, we have so many homework assignments and projects and exams kind of stuff, right? So if it looks like you're kind of going low, talk to me. It's easy and hard in both ways. I mean, you can't argue that something really killed you at the end, but I have a much more broader view of where you stand in the class, right? Make sense? So we are going to the next sort of the big module on storage, right? And storage would appear a lot like the memory module. It's sort of like memory module, except it goes into persistent storage. It goes into a disk or something where it stays for a while. So some of the things that we did for memory module, we can try to move it here, but we also have to make sure that they can survive for a while, right? So before we go into this module, I hope you appreciate the last module we looked at, the memory module, right? It's one of the memories, one of the stuff that could really kill your program performance. When you write a program, the CPU is sort of what the vendors sell you at. I mean, they sell you a machine which is 2 gigahertz or 1 gigahertz or what have you. But the one that really kills your performance is the memory, right? Because it does not matter how fast your CPU can go. It only matters how fast you can feed it data. And as we saw in the module, it's not a simple matter of you want this memory, you got it. You have to go through all this, logical to physical translation, which adds its own complexity and all those things. So things like the cache size you have, L1 cache, L2 cache, and how you write your program, how you organize those things have a significant impact, right? It's so bad that if you don't have something in main memory, if it has to come from the disk, it could be 10,000 times slower. So even if you have a really fast processor, unless you can feed the data, you can't do much. And so the modern machines is not a simple case of you buy 4 gigs of data. It's not like they put all your programs right next to each other, right? They try to bring in all this stuff. So that's one of the reasons why when you buy a new lots of memory, you don't suddenly notice that you can't go into your task manager or something and see that all your programs have all the memory. I mean, the system tries to manipulate all the stuff. The more memory you give it, the more complex it can do, and it's an ongoing process. But essentially, if you as a programmer can work with the system, if you understand what the system does, you write a program which can use those things, you can get the true performance, right? Make sense? So the next module, of course, is storage. And if you have any questions about the grades, talk to me. So the notion here is storage, right? And most of you have used storage. Most of you used files pretty much from day one. So I'm going to sort of go through this chapter really fast because it basically tries to kind of articulate all the things that you sort of have experienced, right? And hopefully I'll use this to explain how to do the homework project in the next lecture. This homework project is either really easy or is really hard, depending on how you approach it, right? It's really easy once you figure out what is happening, right? But it's really hard if you try to figure it out on the last day before the project is due, right? It's true for all projects, but especially it's true for this project, because if you, from prior years' experience, if you haven't thought about it and you try to do it at the last moment, you're going to be in real trouble, right? So start early and finish it off as soon as possible. And one other comment about the homework, the project reports. The TA mentioned some of you look like you drew the graph in color and printed it out in black and white and turned it in where the TA couldn't really tell what was what, right? Because the colors were really awful. So one of the reasons I want you to make the printout is I want you to make sure that you can read the printout, not the ones on your screen, but the hard copy. So please, for your next report, either plot the graphs in black and white or print the graphs in color if you have it in color. But don't have the graphs in color on your monitor, but the printout is something that if you can't read it, the TA definitely cannot read it, right? And if you can't read it, then you'll lose points and stuff. So make sure that the reports are readable by you before you turn it in, right? So we'll look at some of the notion of file systems and notions of files and directories and so on and so forth. So you can think of a file is a logically persistent memory, right? That's one way to look at it. So essentially, if you create a file, you create this logical address space, you create a logical segment or what have you, but you want this to be persistent, right? You probably never thought about it that way, but there are a lot of abstractions which makes it think like that, because if you think about it that way, the virtual memory and the storage is practically the same, right? You're trying to create some sort of some data structure, some segment, but you want them to be persistent, meaning that you want them to survive your system crashing or what have you. You potentially want them to live forever. So that forever choice affects what we do, because we want to make sure that all the data structures are fine, right? All this. So far what we talked about, if you mess up really bad, I mean, you don't want to do that. If you mess up, you can reboot the system and you're kind of good to go. In this case, there's no, you can't escape like that. So if you write something onto the file system, it's going to survive, it's going to be there forever and ever. So you want to make sure that all the things you do are consistent and all those things, right? But otherwise, you can think of this as a large chunk of memory. And you can either think of this as something unstructured, something as a big array of bytes, or you can think of this as something which has structure, right? You can think of this as structure where it's line-based, or you can think of it as field-based, sort of what you do with the Excel kind of things. So, or you can think of it as having more complicated structure. So if you think of your program, right, your program has all the segments we talked about. You have all these segments. So there is some structure to read those files. So you can think of it either as a set of bytes or all these different notions. And throughout the history, we keep going back and forth, right? The first model is pretty simple. You just think of it as a set of bytes. And the more complicated model is you think of them as having a lot of this structure. The real key then becomes who should understand these different structures. Should it be the operating system or the application? right? There are some files which have structure which operating system have to understand, like your program, right? You write a program, your program has all these data structures. Your operating system loader has to know all the structure, it has to be able to read all the stuff. So it's no longer a file which is just structureless. There are some files which have structure which an application needs to know. For example, if you have a Word document or a PDF document, your PDF reader has to know how to read the stuff. It has to put these different arguments. You can also think of files as like a database, right? And this used to be supported in the earlier mini and mainframe computers. For example, VAX VMS file system did support a notion of a database concept, right? So each file you create, you can tell the operating system, I want it to be an index file, a relative file, or what have you. You can do queries and stuff as if you're dealing with the database. Then it went out of fashion when we went to Unix, where everything was considered to be a string of bytes, and then you make some structure out of it in ad hoc fashion. And it's coming back in vogue because the Windows Vista, which is supposed to have WinFS file system, was supposed to bring back database notions, right? And it's been pushed to the next version. So essentially, you keep going back and forth. But regardless of where you do that, the simplicity of having a file with no structure and you figuring out how to deal with it, or the complexity of pushing all the stuff into the operating system so you can get some performance, is something that you worry about, right? So regardless of how you do it, you want to create this data, then you want it to be flushed to the storage, and you want to be able to read it again and again, right? That makes sense? And you might have seen a whole bunch of different types of files, and many of the systems deal with the types as extensions. So if you see a file which has a .exe, and if you're running on Windows, it knows it's a different kind of file. So it knows there's a certain organization to it, and it uses that to make some behavior. So if you click on a .exe file, it'll run it because it knows that this file is not just a set of bytes. It knows there's a structure. It knows how to read it, right? And there's all these other ones, like there's a .o and .obj and cc and bat and all those things. Each of them, there is no rhyme or reason why .exe has to be an exe file, right? You can create a file using Word and call it .exe, but it's a convention, and that kind of helps it. But there are all these different types and all these different ways of organizing data, right? So in terms of, if you think of a file is this notion, right? A file is this thing that you store, and it has lots of attributes, and attributes depend on the different operating system. And at the least, it has a name, right? One of the things that you have is a name. So for example, you have etc. password, or so all these files have a name. And there are other attributes like identifier, a unique number that is used by the system to figure out what that file is. It's sort of like when you talk about processes, you have a process ID, or so that tells you what the file is. So you may have different names as you choose to use it as a user, for convenient for you, but underlying system may have a unique identifier that is used by the file system to figure out where things are, right? So there's a notion of a type. So if you're on an operating system which supports type, it may have this notion of a type, right? It may be a simple notion where every file which is .exe is known to be a certain type, or it can be more complicated, right? So if you used Mac, right? Mac creates a whole directory into a file and then does certain complicated stuff to figure out what the object type and what you should do with that, right? And then we need the notion of a location, right? To figure out where you actually stored this file. So you need to have a notion of a file and where it is stored, and we'll see how you would manage those concepts. The size of the file, and then the notion of a protection bits, which since these are persistent, right? So the key thing to remember is when you create a memory, when you allocate a memory, right? It can create it as something that is private to you, and the operating system can keep track of who should have access to your program in memory, right? With the idea that if the machine was ever to crash, everything is lost, it doesn't have to keep track of anything like that. Whereas in this system, when you talk about files, if you create a file, the operating system cannot remember those somewhere else. It has to write everything into the storage, because when you reboot the machine, it has to keep track of all the stuff. It has to remember all the stuff, right? So it stores stuff like protection, who owns it, who creates it, who can read it, who can write it, onto the file, not in the operating system itself, but into the file. So next time somebody comes in, they can look it up to see who's supposed to be able to read it, who's supposed to be able to write it, right? So things that we kind of didn't do before, because in the memory concept, if a system was to reboot, you don't particularly care what the permissions were, because you're starting afresh. Here it's not the case. You need to write the protection into the files. And other information that most of you have seen, like time when it's created, time when it was accessed, and other services which are useful, who created it, and how many times it's used, and all those things. And again, all of this have to be kept with the file on the storage, mainly because when the system was to reboot, you want to make sure that you can still get access to the same things, right? So to give you an example, if you do in the Unix, if you do ls-l, it gives you a bunch of attributes, right? And if you, depending on the flags that you use, you can see different attributes. So ls-l I tells you what the inode number is, which is the file ID that the system knows. And we'll see what that is in a little bit. So essentially the number 2604 is the ID that my system knows this file as. And then you have the issue of what are the privileges. We'll see what those are, like RW and all those things. Who created it, what's the group, and what's the file size, when it was created, name of the file, and so on, right? And if you use more of a GUI-based system, you have different attributes. Like for example, in the Mac, if you look at a file attribute, you have all these things, and you have this notion of who has access privileges, and it kind of knows the types, so it knows who can open this file and all those things. Which is all part of the notion of a file, right? So essentially, it's the memory thing we talked about. We're kind of extending it to make it permanent, and that's the thing to remember, right? So once you have a file, so if you think of this as object-oriented sense, you have to define notions of what are the operations which are possible, right? So if you develop an object-based file system, which people have tried over and over again, and with varying levels of success, then you have to define what are the operations which are possible on a file, right? So what are the operations you think are possible on a .exe file? .exe in Windows is an executable file, right? So what are the operations you think you would want on a .exe file? Run it, right? So the fundamental thing you want is notion of execute or run, right? And then you may have other operations like read and write or what have you. But essentially you want the run operation, right? So if you assume like a Unix kind of file system where the system does not really have much structure, you can think of these operations as more important, right? Which is supported by most operating systems, which is the notion of create, right? Which will create a file, and write, read, reposition. We'll see what that is in a little bit. Delete, truncate, and create may also be called open, right? Create/open. So depending on whether this file did not exist before or if it exists before, if it did not exist before, open would be considered to be a create. If it did exist before, open would be considered to be a open. I mean, open something which existed before. So essentially, when you say open a file, you would have to search through some data structure to figure out what file you're talking about, and you open it. And when you say close, you have to figure out what file you're talking about, close it, so you lose all the structures, right? So all these operations translate into something that you can think of in POSIX-C. These are the operations that you think of it as an object-based system, but these translate into something that you will use with the, let's say, C, right? So what would a create translate to in C programming language? If you don't remember off the top of your head, create is essentially, some of the systems actually call a function called create, but it's essentially a thing called open, right? If you remember, if you created files, remember, this is what you do in C, right? You do open, you have a path, right? Then you have flags, then you have mode, right? You remember, this is how you create files, right? You may either call it as open, or you may call it as fopen, which is a library function which essentially calls this, right? In fopen, you'll give a path, and you give mode bits like read, write, or what have you, right? So this translates into the system call. So this is what you worry about. So this flags, right? There's a whole bunch of flags. If you said something like O_create, one of the flags, which means that if the file did not exist, create it, right? So that would be something that you consider to be a create, and you have other typically use 3 flags, right? One is create a file if it did not exist. One is truncate a file if it exists, truncated, and the other one is append to it, right? So if you add these 3 bits, this is again when you write a C program, right? This essentially says if a file did not exist, create it. If it existed, make it 0 bytes and start fresh, and add to the end, right? So these 3 operations to open would sort of make it a create operation. So if a file exists, create a new file, right? So from your program, when you say something like this, essentially you are creating the notion of creating a file, right? So what is the stuff for write? Yes?
I had a question about the flags. Are they doing the same thing as the mode operations, like the R, W?
No, those go after here.
But I mean, how are they saying different? Aren't they talking about the same information?
No, so we will see the modes in a little bit. But essentially here you would say, I forget what the, I think it's something like this, s_u read, right? Which means that user read bit, right? So you can say s_user, you have to see what the flags are. So you set the modes here on whether you want the user to be read, write, execute, and all the permissions you want. So that's the third argument, right? So that will set the mode of the file, the ownership and the operation modes of the particular file, and that goes as a third argument, right? And you could ignore this, and in which case, whatever is default to your system, to your user login, which comes through a thing called umask, which is a user mask. So every file you create would inherit whatever is the umask, and it goes here. So if you don't explicitly state it, whatever was assigned to you, you would set it, right? again, this is a POSIX C version of it. So essentially, you write a program with a certain number of bits, and that translates into whatever you think of as the object operations. So what would be for write? It's write, right? You used write, and you have read, right? The reposition within a file is called seek or lseek or fseek. You may or may not have used them explicitly. And there's also a variant of read and write which combines the notion of a seek, which is pread and pewrite. You'll use that for your program. Essentially, read and write would read the next byte from where you are by default. But you can say, I want to read byte 10 or byte whatever, so you can kind of randomly access whatever. using pread, pewrite are the seek notions, right? So you have a notion of a delete a file too, right, which is usually called unlink, and truncate, which could be done something like this. You open a file with a truncate bit, so the file gets truncated, right? So essentially these are operations which you've used all the time. So these are operations that are operated on the particular file, right? And the main thing to remember, which is different from what we did before, is all these things have to be persistent. So everything has to be returned. If you forget to write something on the disk, then it doesn't exist, right? So if you don't take care to flush everything to the disk, things may vanish, right? So when you open a file, right, somebody has to keep track of some operations, right? One of the things is, I mentioned when you do a typical read, you read from wherever you left off. So if two people are reading the same file, you want to make sure that two people are reading the file, which means that you have to make sure that if somebody wants to truncate it, you have to figure out what is the semantics for two people destructively or constructively interfering with the same file. And as we will see, it varies quite wildly, especially when you go to distributed file systems. We're not going to talk about distributed file systems here, but the same notions we talked about in terms of sharing some two memory segments apply here. But the main thing you need to worry about here is when two people are accessing the same file, if the file happens to be on the same system, there are certain things you can do in terms of what you can guarantee. If they happen to be on a different system, like a distributed system, which we didn't talk about in this class, then there are a lot of guarantees which you can't give. Or if you give the guarantee, the system will be extremely slow. I'll give you a little bit sense of what it is towards the end of this lecture. But so you have to understand what the semantics are for sharing, precisely because these things are also slow. The files are slow, disks are slow, and they may be on different machines and stuff. So some of the guarantees that we took for granted on the memory side, you may not be able to give. But you have to keep track of all the stuff. So I need to keep track of, there's one process which opened a file, another process opened a file. This wants to write it, this wants to read. I want to make sure where you are in terms of the file pointer. So when you issue the next call, I can give you the right set of stuff. And sort of underlying all this stuff is disk is slow, so you want to read from the disk, right from the disk. But if you're reading directly into the disk and reading directly from the disk, you are not going to make progress, right? So you will want to do the same thing we talked about before, which is notion of caching. So if you want to read something and somebody wants to read something, you want to be able to read the stuff, keep them in cache, right? And operating system gets involved. It has to keep track of this buffer that is shared by two people, and it wants to make sure that it's consistent, right? It's the same thing that we did before, two people sharing the memory. But now, if one of you modifies it, I have to know precisely what is the semantics of when it goes to the hard disk. If I don't define what that is, then if two people are modifying the file and something happens, then it becomes undefined, right? So can you think of reasons why you have two processes sharing or two processes writing into the same file? Have you ever written a program where you write into the same file? Let's make it simple. Have you ever written into the same file when you're doing threaded program? It does not have to be threaded. It could be multiple processes. But have you written into the same file in a threaded program? You might have written to it without realizing it. One of the files you wrote was your terminal output, right? If you do a printf or something, if you're printing something from two of your threads, they're basically going to the same file, right? So essentially your printf is a file, your screen is a file, right? So when you write these two things, you want some sort of a, how many of you notice that things get kind of jumbled up and you get some undefined stuff, right? We had that for the pin program, right? The pin program was writing all over itself, right? So that's the same, that's some of the issues. So you want to know precisely what should happen and how to deal with those, right? You write into the same file a lot more than you realize, right? files are the way for two processes to communicate within a system for the most part. So there are two different uses of files. One is a file which is used for persistence. Another one is temporary persistence, right? So when you talk about the compiler, it does the compilation, writes into a file, and then it calls the next program which takes over from that file, right? So for example, when you want to print something, your program writes into a file, calls the print spooler and say, now print this file, right? So even there you use a file, it's pseudo persistent. You don't want this to last forever and ever, but you want this to last enough time so it can be printed, right? So there are a lot of cases where you do this kind of sharing, so you need to understand what exactly happens. So all the systems, somebody has to keep track of who opened it, where are they, what are they doing at which point. And when all of them close the file, I can free up the buffers, I can free up the stuff, right? And which brings the issue of locking, right? So this is again the memory concept. When you have two people trying to modify or trying to read the same thing, you would want some sort of a locking primitive, right? So what kind of a locking can you think of in terms of files? Do we want some of the things it's here is mandatory locking or advisory locking, but before that, do you want the file, if two people want to open the same file, do you want to prevent one from opening as compared to the other one? All the time, certain times. Can you think of a case where you want to prevent people from opening the file? Yeah.
Well, like, if they're just reading, you don't really need to prevent them from opening.
Yeah, so the locking depends on what they want to do, right? So if two people want to read, the reader-writer lock notion comes in here. If two people want to read, it's okay. If one wants to write, then you have to figure out what the semantics ought to be, right? And there's also a notion of a mandatory lock, which means that every time somebody opens it, they have to lock the file. There's also a notion of advisory locks, where the files may be locked depending on what you want to do, right? And for the most part, we go with the advisory lock, mostly because in distributed systems, it's very hard to do mandatory locking, right? Most of you use file systems. You probably use distributed file systems a lot in your career here, right? Can you think of a distributed file system that you use on a day-to-day basis? Yeah, most of you use AFS, right? Which you may directly use it through converters on your Windows machine, right? And you may use Windows file shares or Samba and all those things, right? The true scope of what AFS can do is way beyond the scope of this class. I mean, that's a distributed file system, right? And so essentially the idea here is AFS has lots of servers in which provide service for lots of users, right? AFS is a global file system, right? AFS, you can use AFS from Notre Dame to access something at Stanford or whatever by going to /AFS/Stanford.edu or something, right? So when it's at that scale, the timing issues come in. So you can't really do mandatory locking, which means that every file has to be locked before you can proceed. Because potentially anybody in the planet can be accessing your file if they have the right privileges, right? Mandatory locking would mean that I need to make sure that nobody else in the world can, I want to make sure that nobody else can open the file while I'm doing this stuff. And that can be very slow. So typically you go with advisory locking, where you kind of hope that nobody else is using it, kinds of stuff, right? Which, all the things which you didn't have to worry about in the memory case, now you worry about because things get to be too slow, right? So next is the notion of an access method, how you access the files. The first is the notion of a sequential access, which is sort of what you tend to use, right? Which is you read and write, which basically means that as you do read, you read the next set of bytes, right? So if you do 10 reads, you read the 10 consecutive set of bytes, right? And so you can also think of reset, right? So where you go to the end, you can sort of reset. This is sort of like how you would read from a VCR tape or something, right? So where you kind of keep reading, you keep moving forward, and if you want to read from something, you have to reset it, which is sort of what, like most of you read the file. You open a file, read, close, or open a file, write, and close. But the other mode of operation is to specify where you want to read, right? So you can say, I want to read from the nth byte. So I can use that to kind of jump around the file. I don't have to read sequentially, right? And using this, you can implement some nice things. So thinking of the sequential access, you read the files a certain way. So you read it, the next byte, and so on and so forth. And you can implement the sequential read using the other one fairly trivially, right? So if you want, the reset is basically you go back to the beginning of the file. Reading next byte is you keep track of some pointer and then seek to that address and read this stuff, right? Where these things come into picture is in terms of performance. If I know you're going to read sequentially, then I can do certain optimizations in terms of what I'll bring it from the hard disk into memory, and we'll see those as we move along. So this chapter is basically talking about all the things that people do with files, which many of you have used, whether you realize it or not, right? How many of you use the seek primitives? Few of you, right? Seek primitives are a nice way to kind of jump around the file to read exactly what you want. So that's the notion of a file, right? So somehow in the files have this operation and stuff. Next, you have a notion of a directory, which is essentially some data structure which keeps track of where the files are. The directory is the one which keeps track of files. So when you want to open a file, you talk to the directory and you figure out where the file is, right? The directory knows everything about all the files. The directory knows which file is where, and it keeps track of these. And they also reside on the hard disk, right? So they have different. In terms of files, directory looks like a file, but you have to be a little bit more careful with the directory entry than you do with the file entry, right? Can you think of a reason why directory entry would be a little bit more finicky than a file entry? Think of what would happen if you forget to write something to disk, right? How many of you had a case where you were writing a file and then your machine crashed halfway through, and so you wrote, let's say, 10,000 bytes, and your system crashed? How many of you had found cases where you didn't exactly get 10,000 bytes, but a smaller amount? How many of you seen those? So what did you see? If you didn't see 10,000, did you see like 9,000, or did you see 0 bytes, or remember? You see different stuff. I mean, depending on where exactly things fail, you see the 0 bytes or a few thousand bytes or whatever, right? So what would happen if you forgot to write something on a directory entry? Directory key knows everything about the files, right? So if the directory did not go through, then it does not matter what the files are, you lost it, right? So if you write a big file and every bit of the file actually went to the hard disk, is stored, but if the directory entry is not updated, then the whole thing is lost, right? So you tend to be more careful with the directory. We'll see how that is, use logs and stuff, but essentially you're trying to, so as long as your directory entry is there, you can access a file. If the directory is lost, then the file is lost, right? So you kind of separate them out and you treat them sort of differently because directory entries are not that big, but you want to, so they keep track of all the files which are in the system, right? And then you have a notion of a file system organization. We're not going to talk too much about it right now. We'll come back to that later. The idea here is you may not want to create, you may not want to take a hard disk and then treat them all as one sort of collection. You can create them into partitions, right? So you create them into partitions and have each partition be treated differently, right? So you can call, let's say 2 partitions. So each partition has its own set of directories, right? Or you can treat them as all as one partition. It's a way for you to kind of manage your collection, right? So you don't want to, so you may want to say keep your operating system on one partition, user system on another partition, right? And that's your way of convenience. But essentially, you want to create these different partitions, And we call all the things, the directory and the files which belong to this one collection a file system, right? So this file system, whichever way you organize it, has a set of directories and files associated with it. So in this particular disk, there are two different file systems, each treating a different set of files with a different set of directory organization, right? And that's the notion of file system. So you have a notion of files, you have a notion of directory, which essentially keeps track of all the files in the system, and together you call them as a file system. So you can use a file system to access all the files and directories on a particular collection, right? So in terms of the directory, right? So directory keeps track of all the files in the particular file system. Again, you have a set of operations that you can do on that directory, right? And those are sort of intuitive. So the first operation you need is search a file, right? Directories are there to give you information about a file. So you need to be able to find a file. So if I say I want to look up a file called password, directory entry should be able to tell me whether search and then find out whether the file exists, right? If it doesn't exist, I need to have a notion of create a file, delete a file, rename a file, and list a directory so I can kind of see what the files are, right? So in terms of all these operations, when you do a ls password, you're kind of saying list file called password. So search to see if there's a file called password and let me know about it. And create a file is part of when you do a create file call, you have to tell the directory that now I'm creating a new file called path and store it, right? And this will be called thing called make node. And we'll see how all this relates to your homework project in the next lecture, right? And delete a file, which when you unlink a file, you have to tell the directory that this file is no longer exists. And list a directory where you don't know which is out there, so you want to see all the files in a particular directory. Typically you do ls minus l or something, or in Windows you do dir or something, and you see all the files in a particular directory. And rename a file or traverse the file system, right, to go through all the file system to find what the files you're looking for, right? So these should be intuitive because you've been doing this pretty much most of your career, right? And the challenge here is to figure out how to organize the directory, right? How would you organize a directory if you were to implement this? Your goal is to implement a data structure which keeps track of a bunch of files, right? And you can search them on the name, and you want to keep track of the structure, right? So what data structure would you use to manage this directory entry? Thinking back at your simplest data structure, right?
A tree? A tree?
Yeah, you can think of a tree. You can think of a B tree or what have you. You can think of a simple, just a linear list of stuff too, right? So as we'll see, there's no magic here. It depends on how you want to do it, right? What does it depend on? How would you decide what data structure to use for the directory entry? Directory is very simple. I mean, it basically has a list. It's basically a table of names and the file attributes, right? When would you decide to make it a pretty complicated data structure? When would you decide to make it a simple data structure? Yeah.
You want to make it more complicated if we're going to like separate files by user or yeah, basically.
And the other reason, yeah, so depending on how you access it, right? If you have lots of files in a directory, you'll find that you have to make it more complicated, right? So how many files do you think are in a typical directory? You use machines, right? How many files do you have in a particular directory? How many files do you think you'll have for homework project 4? Not the exact number, let's say tens, hundreds, thousands, millions. Tens. So how many, so if you use Windows, right? So Win32 directory, how many files do you, how many of you seen, how many files are there in the Win32 directory and all, right? How many files do you think there are? There's usually a lot of files, right? Maybe thousands of files, right? And those files get accessed a lot, right? So you want to make sure that those things can be searched and found quickly. So you don't want to do a linear search or whatever, right? So again, it depends on what you're trying to do. So if you try to use the files the way it's not designed to, you'll see horrible performance, right? If you use a linear search and you have a million files, you're practically sitting there looking at the directory all the time, right? So there are different ways of organizing directories. None of you may know any other way because we've kind of settled on hierarchical trees, right? But back in the days, there used to be a time where there only was a flat directory structure, right? There's no sub directories. So all the files kind of were hanging off of this one root, right? So if you were to access it, basically you have slash and that's it, right? All the files existed off of there. So you created this one data structure. This was good when there were not that many files. Back in the days, there were not that many files. So it was kind of simple. You have one directory data structure, and off you go, right? To search a directory, right? You have to. So again, everything is in the hard disk. If you're thinking of this as a hard disk, right? So if you want to look for a file called test, I would have to first read the directory to the disk to find out where the file called, let's say, data is, and then I find where the data is, right? So if the number of files is small, let's say in tens or maybe hundreds, this may be acceptable, right? We don't see this typically in real life on desktops and stuff anymore, but you might find this on a cell phone or the simpler cell phones, right? So it's easy to keep. There's only one data structure called directory data structure, and files are there. There is no organization to it. You can only have one name in the whole system, right? So for example, if you create a file called data, that's it. Nobody else can create another name called data. This is not very flexible, but it's a very simple approach. Another way, which BMS and all used, was essentially created a two-level hierarchy, right? Where the first level is a username, and second level is sort of what we had before. So essentially, for each user, you have a flat tree. Now, different users can have the same file called, let's say, data, but you can only have one file called data, right? So user 1 can have something called A, user 2 can have a file called A, and user 3 can have a file called A. But within that particular user, they can have only one user, right? So this makes it a little bit more complicated. Now I have to find out first where the user is, and then I have to find out what the files you have. But it's still a simple data structure. Realistically, now we went into a tree data structure, right? Which makes it much more interesting because now I can have different names depending on where I am, right? So for each of the tree nodes, I can have the same file called A, right? It's much more flexible than what we had before, but it also makes it more complicated, right? Which means that now I have to have a way of traversing the whole tree, right? So I may have to call a file called, if I have root as slash, I have to say from the root, give me directory spell / mail / copy / all / whatever. So I need to do multiple directory lookup. I need to first look up that directory, and then the next level directory, next level directory, next level directory, and so on and so forth. So it's much more flexible, but then it adds this complexity of having all these directories, right? And we'll see why this is performance hit when as we move through the module. Essentially, all of this have to be on the hard disk, right? Because all this have to be persistent. So if I want to look up something called spell, right, I would have to first look up where the root is, where the mail is, where copy is. So I have to read that directory entry, which means I have to read a bunch of disk blocks. Then I have to read the next directory entry, next directory entry, next directory entry. So potentially this could be a disastrous thing because I need to read a whole bunch of disk. And of course, this is where our whole caching will come in, right? So it's flexible. This is what we use. Most of the machines that you use follow this model, but there's a penalty to be paid for doing this stuff, right? We'll continue with this on the next lecture. So I'm kind of going through this section fairly fast because this is, at least for the initial parts, you must have used files, so I'm assuming you understand. If you don't, let me know, right? I'll see you on Wednesday.